ask for the proportional. So we have to select the disturbance in the range of the regulator. Yeah? And of course, we have to select a proper range of let's say, proportional and integral to make the simulation. But it is important as well to do a simulation with proportional and integral, really with the regulation strategy we are using. Because if we are regulating impedance or arc resistance, we are talking about parameters in the range of, let's say, 10 millions. If we regulate the current, we are regulating parameters in the region of 60 kiloamps. And if we regulate the voltage, we are regulating parameters of about 200 or 300 volts. So it's not the same range, so you will not have the same proportional. So then this diagram explains that we are doing a lot of, let's say, simulations with here in the z-axis the equation, and here the integral time and the proportional time. And of course we will select the optimum here, or the minimum value of this stuff. The other interest of this function is that we can calculate time by time the feature of the mechanical system. And for example, sometimes, I mean, not for startup, but for, let's say, regular base for the customer, the furnace results is going down and nobody knows why. That can be scrap, that can be oxygenless, that can be, and most of the time people are saying the regulator, it doesn't work correctly. Because it's an easy way to say, I don't know where the problem is, but for sure it should be the regulator because it looks like a black box. In fact, the regulator is all the time working very steadily. Because it's the same software, there is no reason to change anything. In the past, with the analog regulator, maybe some component may be damaged, but nowadays the program with the PLC is not the question. So in fact, this is the mechanical system which may have a trouble. It means hydraulic valves or the mechanic of the electric arm itself. So you're running this identification program from time to time, and it gives you an information really on what's going on. If you have, let's say, friction, you will see in this diagram. Because the hysteresis will be very large, and that band will be, let's say, increased. So you will see this on the diagram. If you have air in the cylinder, you will see as well here, because you will have swings. So you will have modification of these main parameters here. So it's a tool for, let's say, diagnostic of the mechanical system. I remember in several steel plants with a good management team, the electrode speed control was done once a month. Maybe not in Indonesia. So it's a very powerful tool. And for sure, if you develop this, you will be almost the only one to have it implemented. So data recording. So you have two kinds of information. The real time, because the regulator is able to store every second all set of parameters, and the average values per basket or per transformer tap or per heat. So I give you an example of let's take this is an example of heat report. Okay, there is just one tap. It's a bad example, but there is just one tap. So this is the basic information of the heat with the average figure for the heat here. And then afterward you have all electrical parameters. This is an old version. I should have oh yeah, yeah. Why should I don't go through my document? It was a very good document actually. So you have all a kind of report, yeah? So maybe some parameters are not clear to you. The two-phase operation. I mean, we calculate during the heat the proportion of the time on the power on time where we have just two phase. That means one current is missing. It gives an idea on the good tuning of the regulator. Because this should be below, let's say, 3%.
Two phases of operation.
Well, otherwise everything looks clear. Stability index, you know. There is a control deviation here. This represents the standard deviation of the output signal. Yeah, and if we look on the average, it should be all the time going down, because the electrode has a tendency to go down during melting. And during the melting phase, main melting phase, you have, let's say, up and down, and during refining phase should be zero. So if you have a huge standard deviation, for example, like 20%, it indicates either that it is the boiling phase, or you have a problem with something in the furnace. Maybe the scrap is not good, or there is, let's say, mechanical damage.
So when you calculate the impedance and resistance and electric powers, and we can compare the result and our operation using the test data.
You mean the results? These are the results? Yeah.
So we calculate the impedance.
Which calculate?
From transformer to
which calculation?
Impedance.
Yeah.
And resistance. And stability.
What do you mean by calculation?
Yeah, we have to do calculation of the total impedance and resistance from the transformer to the electrode. And then we also can simulate using the impedance program.
You want to check the model?
And then we design and we check the result.
Yeah.
Compare using this data.
Yeah. This is is not the main purpose of this report.
Yeah.
The main purpose of this report is to check if the furnace is running well or not to check if your calculation of it.
Yeah, but we are using some calculation and
Okay. If you want to do it once and when you are convinced that the calculation is good, you don't do it anymore. No, the main purpose is to see
the main purpose is that other.
how the furnace is working. And whenever you change something in the regulator settings, then you see the results here. Current and balance, not very good. So this output signal compared to the standard, to the control deviation, this is the average. This is not the standard deviation. Here is the standard deviation. So this is the average of the square, and here this is the complete average.
Yeah, please.
Output signal. This is the average. So you see, it's minus because they have a tendency. Up and down in a second. So, I didn't give any information how to organize the heat reports, because I expect that you will have good ideas how to do it, and better ideas than what I've seen up to now. What I know is that some suppliers are providing a database that maybe it's a big hammer for a small fly. It's a very huge tool for a small purpose.
뼈다가 꼭 그런 데이터베이스는
Because it may be interesting to look individually, but most of the time we are looking, let's say, a set of heats. For example, this is not a good. So, just not finished. So you put all the heats in a big sheet with all parameters like that, and then you can calculate some mean values. Okay, then it's not finished. Finished it up. You can calculate the mean values per phase, per transformer tab. You select the transformer tab you wish. You have still mistakes because not finished to develop. And you put some filters here because this is on Excel. It's easy to make the database. You may have also some other statistics. And display. It's a distribution of the power of the current, here the active power and the standard and the stability index. And normally I should be able to select the parameter I want. was the power on, I take the arc resistance, and it's changing the diagram. You see, this is this kind of formulation which is very useful. To have it in column, and each line is one heat. So as well, this is the heat report, and what you see on the data scope. You remember on the data scope you have the real-time values of the parameters, and this could be stored as well and be used later. Then we go to visualization. So we have talked about this visualization this morning. The scope. This is the space of the identification, which I don't have in PDF because it was not finished. So we select here the electrode, and we start. We go to the start position, which is in the middle, and we make the sinus identification, the response time identification, and then the correction, the simulation, the optimization. Configuration. Okay. And finally, what is important is to have a fast acquisition mode. Because the I/O cards of the normal PLC are not fast enough to have good accuracy. Okay?
Okay. 끝났네. It's the end.
N. I don't have a screen with N.
이거 가지고 PLC 프로그램마다 얘를 낼까? 그건 안 되거든요.
You are just missing the PLC program.
But PLC programmers, PLC can understand all of things, and can you make a program with this?
With this fucking shit, you mean?
I know. I don't like the program.
Are you able to understand this document?
No, that's all.
No? What did you understand?
I understand this also briefly.
Huh?
Briefly. But if I do program, I
Are you able
this.